Welcome to This Explainer. I am so glad you're tuning in, because today we're looking at a piece of hardware that honestly absolutely defies traditional engineering logic. Based on a really fascinating recent analysis by tech writer Aaron Rose, we're going to explore a wild story of manufacturing impossibility, massive computing power, and a high-stakes financial play that is completely reshaping the future of artificial intelligence. Okay, let's just dive right into it.
So to understand why this is such a huge breakthrough, we kind of have to look at how chips are normally made. Pretty much every chip you've ever used, whether it's in your phone, your laptop, or some massive server farm, starts as a large, circular 300mm silicon wafer. Engineers traditionally design the circuitry, and then they slice that single wafer down into hundreds of tiny identical pieces. Each of those tiny pieces becomes a product. But a company called Cerebras looked at that standardized process and asked a truly radical question. What if you just didn't cut the silicon? Like, what if the entire wafer is the chip?
And well, that question led to this absolutely mind-bending number. The Cerebras WSE3, or Wafer Scale Engine 3, features an unbelievable 4 trillion transistors. By keeping the silicon as one giant dinner plate-sized piece, they managed to pack 900,000 AI-optimized cores and 44 gigabytes of SRAM directly onto a single chip. It is literally the largest piece of silicon ever successfully manufactured for computing. Just incredible.
What we're looking at here is a complete paradigm shift. On the traditional side, you've got the standard philosophy, slicing your raw material into small, manageable units. But on the Cerebras side, a single 300mm TSMC 5nm wafer left completely intact. Because they kept it whole, the resulting chip is roughly 50 times larger than a conventional GPU die. And they didn't just build this massive chip to flex on the industry. They built it to solve a very specific, totally massive problem in AI.
And that problem is what we call the AI bottleneck. When you run a giant AI model on a conventional cluster of GPUs, those thousands of small, separate chips have to constantly talk to each other. We're talking billions of times per second. They're passing data back and forth across network cables, wires, switches, the whole 9 yards. And here's the rub. That communication is slow, and it is incredibly power-hungry. The biggest hurdle in AI performance right now isn't actually computing power. It's the time and energy wasted just trying to shuttle data between all those separate pieces of silicon.
So the real genius here is how Cerebras completely bypasses that bottleneck. By packing enough memory directly next to the compute cores on one giant wafer, the data literally never has to leave the chip for computations. Because of this, the CS3 delivers a staggering 27 petabytes per second of aggregate interconnect bandwidth. To put that into perspective for a second, a single CS3 provides over 200 times the interconnect bandwidth of a fully loaded 72 GPU NVIDIA rack. It's the equivalent bandwidth of more than 1,800 flagship servers, all firing off on one single piece of silicon.
Okay, I know exactly what you might be thinking. What happens if there's a manufacturing defect? In a traditional setup, if one tiny die has a flaw, whatever, you just toss that one small chip away and keep the other hundreds. But if your entire wafer is your one and only chip, isn't a single scratch catastrophic? This is where Cerebras introduces their fail-in-place architecture. Instead of demanding absolute manufacturing perfection, which, let's be real, is practically impossible at this scale, they designed a system focused entirely on architectural resilience. The chip is actually programmed to automatically shut down flawed components and just seamlessly route around them.
To actually make fail-in-place work, they executed 3 specific steps. First, they shrank the individual cores down to just 0.05 square millimeters. That's roughly 1% the size of an NVIDIA H100 core, super tiny. Second, because those cores are so small, they could easily sprinkle extra, redundant cores all across the wafer. Third, they utilized an on-chip fabric that instantly detects any physical manufacturing failures and routes data around them using those backup cores. The result? A system with 100 times better defect tolerance than conventional processors. That's the secret sauce that made wafer-scale manufacturing actually viable.
All right, moving on to powering the beast, the physical reality of wafer-scale AI.
As you can probably guess, a chip the size of a dinner plate doesn't exactly just plug into a standard computer motherboard. The physical footprint you need to support this kind of tech is immense. A single CS3 system housing this massive chip takes up 15 U of standard data center rack space. And the power draw? Yeah, it requires approximately 23 kilowatts of power to operate just one of these units.
I think this quote brilliantly illustrates the sheer physical reality of this machine. As Aaron Rose put it, 23 kilowatts is roughly the peak power draw of a large American house. One AI system, one rack slot, one house worth of electricity. When you're running 4 trillion transistors simultaneously, the energy density you're dealing with is truly, truly staggering.
So how on earth do you keep a chip like this from just melting down? Well, inside a standard 42U data center rack, you can fit exactly 2 of these CS3 systems. And the infrastructure keeping them alive is intense. You've got massive fiber connectivity at the top of the rack, enormous power supplies, and redundant pumps driving a proprietary liquid cooling system. The immense heat generated by that silicon wafer is removed either through high-powered fans or pumped directly into the facility's water cooling systems. It is an absolute masterclass in thermal engineering just to keep the thing running.
Okay, next section. The 20 billion twist. OpenAI's master plan. So recently, Cerebras filed their S1 with the SEC to go public. And buried in those financial documents is a massive revelation about their relationship with OpenAI. OpenAI didn't just buy a few chips from them. They signed a master relationship agreement worth $20 billion for 750 megawatts of inference computing capacity. But wait, that's just the start. At the exact same time, OpenAI loaned Cerebras just over $1 billion via a secured promissory note maturing in 2032. And, explicitly tied as a sweetener to enter this deal, OpenAI received warrants to purchase 15% of Cerebras' fully diluted equity. So OpenAI is simultaneously their biggest customer, a billion-dollar lender, and a massive equity warrant holder. Wild, right? The takeaway here is profound. This isn't just a simple procurement decision where a software company buys hardware from a vendor. No way. This is OpenAI vertically integrating its inference stack. By doing this, they're locking in massive future hardware capacity while building a direct financial stake in the hardware layer itself, well ahead of its own IPO. And considering Cerebras recently went public with a valuation hitting $95 billion, OpenAI is perfectly positioned as a direct financial beneficiary of the very hardware company they are essentially keeping in business. It's a brilliant strategic enclosure.
Which brings us to carving an inference niche.
With all this power and heavyweight backing, it's super tempting to look at the WSC3 and just label it an NVIDIA killer, right? But the reality of the AI market is much more nuanced than that. Looking at the benchmarks, the CS3 is an absolute monster at inference specifically. It runs up to 21 times faster than NVIDIA's DGX B200 on reasoning workloads, all while boasting a 32% lower total cost of ownership. Now, inference is the part of AI that actually serves you an answer when you type a prompt. If you want a complex answer instantly, this is the hardware you want serving it. Cerebras completely dominates when it comes to spitting out model outputs at incredible speeds.
But despite Cerebras having this incredible hardware, here's a quick reality check. NVIDIA still commands roughly 90% of the AI accelerator market share. They generate something like 423 times the revenue of Cerebras. Why? Well, because training those massive AI models from scratch still heavily favors NVIDIA's ecosystem. They've built an incredibly deep moat with their CUDA software. Cerebras isn't going to just replace NVIDIA overnight. Actually, it's more like they're carving out a highly lucrative niche focused entirely on where speed and memory bandwidth matter most. And they are working to completely own that specific space.
To summarize this whole incredible journey, Aaron Rose writes, "The chip that shouldn't exist is publicly traded. And the company that needs it most helped finance it. Cerebras looked at standard chip manufacturing and did what intuition said was physically impossible. And OpenAI recognized that this impossible hardware was exactly what they needed to secure their own future, funding it in a way that totally blurs the line between customer and owner."
Which leaves us with this final, really vital question to ponder. If the creators of the world's most powerful AI models are now heavily integrated and financially embedded in the hardware companies that physically run them, what does this mean for the future of tech monopolies? Are we witnessing the birth of totally closed vertical ecosystems in the AI age? Think about it. Thank you so much for joining me for this explainer. Keep learning and keep asking those big questions.